Hello everyone, I am Guang, and today I will talk about heuristics for CT reconstruction with a particular focus on cone beam spiral CT. As you know, the dominant scanning mode in modern CT is cone beam spiral CT, also called cone beam helical CT. So, what exactly is cone beam spiral CT? In this geometry, a point-like X-ray source and a two-dimensional detector define a cone-shaped X-ray beam. This cone-shaped beam passes through the patient and collects projection data on the detector. At the same time, the X-ray source and detector rotate around the patient inside the donut-shaped gantry, while the patient table continuously moves through the scanner. Because of this combined rotation and translation, the X-ray source follows a spiral or helical trajectory relative to the patient. Along this trajectory, the system continuously acquires cone beam projection data. Today, a very large number of medical CT scans are performed worldwide each year, and the most modern clinical CT system use this cone beam spiral scanning mode. This naturally raises an important question. How do we reconstruct an accurate image from such cone beam spiral data? More specifically, how can we convert this continuously acquired three-dimensional projection data into a reliable cross-sectional or volumetric image of the patient? That is the central reconstruction problem we will discuss. There are now many algorithms for cone beam spiral CT reconstruction. Historically, the development of this field moved from approximate reconstruction method toward theoretically exact reconstruction method. In 1991, I proposed one of the first cone beam spiral CT reconstruction algorithm. That algorithm was approximate, but it was important because it demonstrated how cone beam spiral data could be reconstructed in a practical way. Then, in 2002, a major theoretical breakthrough was achieved by Professor Alexander Katsevich, a Russian mathematician at the University of Central Florida. He formulated the first theoretically exact filtered backprojection type reconstruction, or even for spiral cone beam CT. In other words, it took the field about a decade to progress from approximate cone beam spiral reconstruction to a theoretically exact solution. This was a remarkable development. It shows that despite the complexity of cone beam geometry, spiral source trajectories, and incomplete-looking local data, exact reconstruction is mathematically possible under the right conditions. In contrast to many standard textbooks, here we will explain cone beam spiral CT reconstruction heuristically. That means we will emphasize intuition, geometry, and conceptual understanding before going into the full mathematical details. We will proceed in a natural order. First, we will discuss parallel beam CT reconstruction, which is the simplest geometry. Then we will move to fan beam CT reconstruction, where the X-rays diverge in three dimensions. This sequence is logical because each geometry generalizes the previous one. The parallel beam can be viewed as a limiting case of a fan beam when the fan angle is very small. Similarly, a fan beam can be viewed as a special two-dimensional slice of a cone beam because a cone beam contains many fan beam-like planes. So, by understanding parallel beam reconstruction first, then fan beam reconstruction, we build the foundation needed to understand the cone beam spiral CT reconstruction. In my medical imaging course, I want students to understand the fundamental ideas behind image reconstruction, especially cone beam spiral CT reconstruction, because this is a central part of modern CT theory. More specifically, we want to answer several important questions. How can we perform approximate cone beam spiral CT reconstruction? How can we improve an approximate method and eventually reach a theoretically exact reconstruction? How given cone beam divergence and longitudinal data truncation, how can exact reconstruction even be possible? The paper by Professor Katzevich is mathematically very dense. I still remember challenging my group by asking whether any lab member could understand every formula in that paper within 1 week. That is not an easy task because derivation involves highly sophisticated mathematics. Here, however, I will present the key ideas in a heuristic way. My goal is to guide you through the reasoning step by step so that the exact formula for cone beam spiral CT reconstruction becomes much more understandable. You may have heard of wave-particle duality in physics. In a similar spirit, we will begin with a kind of duality in mathematics in mass periods and signal processing. This perspective will help us connect geometric intuition with analytical reconstruction formulas. Once we see that connection, the reconstruction theory will become much less mysterious. The duality is not only a concept in a physical world. So we also have duality in mathematical signal processing. On the left-hand side, we have a wave point of view. Fourier analysis tells us that a function can be decomposed into a superposition of waves. In other words, a signal or function, such as the red curve shown here, can be represented by adding many sinusoidal waves with different frequencies, amplitudes, and phases. On the right-hand side, we have a particle point of view. Instead of representing the function as a combination of waves, we can represent it as a combination of shifted and scaled impulses. These impulses are delta functions located at different positions, and each impulse carries a certain weight. So, mathematically, the same function can be understood in two complementary ways, either as a superposition of waves or as a collection of localized impulses. This dual viewpoint will be very useful for understanding image reconstruction. If we view an image as a collection of pixels or in 3 dimensions as a collection of voxels, then we are using the particle point of view. Here, the image is represented by many small localized elements. Each pixel has an intensity value, and together these pixels form the full picture. For example, on the left, we see a low-resolution pixelated image. Each square block represents one local image element. On the right, we see the original continuous-looking picture. This example reminds us that digital image is not stored as a continuous function. It is stored as a finite set of numbers, one number for each pixel. Therefore, when we reconstruct a CT image, we are essentially trying to estimate these unknown pixel or voxel values from X-ray projection measurements. This pixel-based representation naturally leads us to an algebraic view of CT reconstruction. Now, let us connect this image representation to X-ray physics. In X-ray imaging, the basic physical principle is Beer's law. Suppose we have an incoming X-ray beam, and let us call it intensity In. This beam passes through a small piece of material with a thickness delta x. After passing through the material, the beam becomes weaker, and its outgoing intensity becomes I out. How much the beam is weakened depends on the material. Mathematically, these attenuation processes can be described by a differential equation. The rate at which the X-ray intensity decreases is proportional to two things: the current X-ray intensity and the local attenuation coefficient of the material. We denote this attenuation coefficient by mu of x. It tells us how strongly the material attenuates X-rays at each position. If we solve this differential equation, we obtain Beer's law. For monochromatic X-rays, the relationship between the incoming and outgoing intensities is exponential. The exponent contains the line integral of the attenuation coefficient along the X-ray path. Now, in a real CT scanner, we can measure both I in and I out. So if we take the logarithm of I in divided by I out, we obtain the line integral of mu along that X-ray path. This is the fundamental measurement in CT. The single pencil beam of X-rays measures one line integral. Now, when we digitize the image, we divide the object into many small pixels. The result, we assume that each pixel has an approximately constant attenuation coefficient. Then the continuous line integral becomes a finite sum over the pixels crossed by the X-ray beam. This finite sum is what we call a ray sum. Each pixel contributes according to its attenuation value and according to how much of the ray passes through that pixel. So in the end, each X-ray measurement gives one ray sum. Equivalently, it gives us one linear equation involving the unknown pixel values. Whenever we send an X-ray beam through the object, we measure what we call a ray sum. Mathematically, each ray sum gives us one linear equation. Let us use a very simple example. Suppose the image has only 2 by 2 pixels. Then we have 4 unknown pixel values. We can call them mu1, mu2, mu3, and mu4. To determine these 4 unknowns, we need enough independent equations. For example, if we send horizontal X-ray beams through the image, one beam may measure the sum of the top 2 pixels, so we may get mu1 plus mu2 equals 7. Another horizontal beam may pass through the bottom row and give us mu3 plus mu4 equals 3. Similarly, if we send vertical X-ray beams, we get additional equations from the columns. One may give mu1 plus mu3 equals 6, and another may give mu2 plus mu4 equals 4. So in this small toy example, the CT reconstruction problem becomes a system of linear equations. Of course, real CT is much larger. We do not have only 4 unknowns. We may have hundreds of thousands or even millions of unknown pixel or voxel values. So the projection data form a very large system of linear equations. One way to solve such a system is to use an iterative algorithm. The algorithm starts with an initial guess of the image. Then it computes the ray sum from that guess, compares them with the measured ray sums, updates the image step by step. After many iterations, the computed projections become more consistent with the measured X-ray data. This is the basic idea behind algebraic and iterative image reconstruction. Now we can ask a more general question. If we collect many ray sum equations, can we be confident that there is enough independent information to uniquely determine all the analogy of peeling a two-dimensional onion to explain this idea? Imagine that the object we want to reconstruct is like an onion with many layers. We begin with X-ray rays that are tangent to the object. A tangent ray touches the object at only one point. Therefore, the measured line integral from such a ray directly gives us information about a single peripheral pixel or a very small boundary region. Once we determine the values on the outermost layer, we can conceptually remove or peel away that layer. Then we move inward to the next shell. Rays that previously passed through both the outer layer and the inner layer can now be corrected because the outer layer is already known. This allows us to solve for the next layer. Continuing this process layer by layer, we can recover more and more of the image. Eventually, the entire two-dimensional object can be reconstructed. Of course, this is a heuristic explanation rather than a practical reconstruction algorithm. But it gives us an important intuition. With enough projection data from suitable directions, the internal image information is encoded in the measured X-ray data. In this sense, Connecticut reconstruction can be understood as progressively recovering the hidden structure of the object from its line integral measurements. Naturally, we can extend the two-dimensional onion peeling idea to the three-dimensional case. In 2 dimensions, we use line integrals to recover the object layer by layer. In 3 dimensions, the corresponding concept is based on planar integrals. Instead of thinking only about X-ray lines through a two-dimensional slice, we now think about measurements over planes that intersect a three-dimensional object. Imagine that the object is a three-dimensional onion. So we begin from the outermost shell. A tangent plane touches the object a very small region, ideally at one particle or one voxel on the boundary. Therefore, the corresponding planar integral gives us direct information about that outermost voxel or shell element. Once the outer shell has been determined, we can conceptually peel it away. Then we move inward to the next shell. Since the contribution from the already known outer layer can be accounted for, the next layer can also be recovered. By continuing this process shell by shell, we can reconstruct the entire three-dimensional object. This is not meant to be a practical reconstruction algorithm, but it gives us an important intuition. With sufficient projection information, the internal three-dimensional structure is encoded in the measured data and can in principle be recovered. For image reconstruction, we can also take the other perspective, namely the wave point of view. From this viewpoint, an image is treated as a superposition of many waves in 2 dimensions. These are two-dimensional sinusoidal waves with different spatial frequencies and directions. The Fourier transform provides a convenient way to extract these wave components from an image. Here, the image of Röntgen can be transformed into its Fourier spectrum, shown in the middle. Each point in this spectrum corresponds to a particular two-dimensional wave component. The farther a point is from the origin, the higher the spatial frequency of that wave. The direction from the origin to the point indicates the orientation of the corresponding wave pattern as illustrated by the enlarged wave field on the right. Therefore, if we can determine the full Fourier spectrum of an image, then we know all of its wave components. Once those wave components are known, we can perform the inverse Fourier transform, which simply adds all the waves back together to recover the original image. So from the wave perspective, Connecticut reconstruction becomes a problem of finding the Fourier spectrum of the unknown object from X-ray projection measurements. Now, the key question is, how can we find the Fourier spectrum from X-ray measurements? The essential tool is the Fourier slice theorem. Let us consider a two-dimensional object represented by f of x and y, as shown on the left. We send a parallel beam of X-rays through this object at an angle theta. The measured projection profile is called P of theta and r. We raise the detector coordinate. And now If we take the one-dimensional Fourier transform of this projection profile with respect to R, we obtain a one-dimensional Fourier profile. The remarkable result is that this Fourier profile is exactly a radial line in the two-dimensional Fourier transform of the object, which we call capital F of u and v. This radial line passes through the origin of the Fourier domain and has the same angle, theta, as the projection direction. This is the Fourier slice theorem. So every parallel beam projection gives us one radial line in the Fourier domain. If we change theta from 0 to 180 degrees, these radial lines rotate through the Fourier space. With enough projection angles, we can cover the Fourier domain sufficiently. Then, by applying the inverse Fourier transform, we can reconstruct the image. This theorem gives us a very powerful wave-based interpretation of CT reconstruction. Now, why is the Fourier slice theorem correct? If you open the textbook, you may see a long mathematical derivation, maybe 2 pages or more. But here, we do not need to go through all of those details. Let us understand the idea heuristically. Look at the figure on the right. Suppose we shoot vertical X-rays through the object. These vertical rays are sensitive to wave patterns that vary in the horizontal direction. In other words, they measure information from wave whose direction is perpendicular to the X-ray direction. Some vertical rays pass through the peaks of the horizontal wave. Other vertical rays pass through the valleys. So, as we move across the detector, the projection profile records the variation of that wave pattern. Now consider a different case. Suppose the X-ray beam is oblique, like the purple ray shown here. Along this oblique path, the ray passes through both peaks and valleys of the horizontal wave. The positive and negative parts cancel each other out. As a result, that oblique ray does not give useful information about this particular horizontal wave component. So the intuition is simple. A projection mainly measures the wave components that are perpendicular to the X-ray direction. This is exactly what the Fourier slice theorem says. A projection taken at the angle theta gives us a radial line in the Fourier domain corresponding to that direction. This is why CT reconstruction can be understood as Fourier imaging. So by collecting projections from many angles, we collect many radial lines in the Fourier domain. Once enough Fourier information is collected, the image can be reconstructed by combining all those wave components through the inverse Fourier transform. The parallel beam scanning is the first generation geometry of computed tomography, or CT. In this geometry, the X-rays travel through the object along parallel lines. So for each projection angle, the detector records a projection profile. You can think of this profile as a collection of line integrals through the object. Mathematically, these projection data are described by the Recon transform. On this slide, we denote the projection data as P of R and theta, where the detector position and theta is the projection angle. The goal of CT is to recover the unknown image represented by f of x and y from these projection measurements. So in simple words, Connecticut is image reconstruction from X-ray projection data. So this slide shows the basic parallel beam model. We have the object represented by f of x and y. We send parallel X-rays through the object. Then the detector measures the projection data P of R and theta. From this projection data, we want to reconstruct the original image. This is the simplest CT geometry. Once we understand this case, we can move on to more advanced geometries, such as fan beam CT and cone beam CT. Okay. Result based on the Fourier slice theorem, each parallel beam projection gives us one radial line in the Fourier domain. So if we collect many projections over 180 degrees, we obtain many radial lines. Together, these lines form a star-like pattern in Fourier space. If the angular sampling is dense enough, this star pattern covers the Fourier domain very well. In principle, we could reconstruct the image directly from these Fourier samples by using the inverse Fourier transform. But in practice, this idea leads us to a very important and efficient algorithm called filtered backprojection, or FBP. The formula in the red box shows the parallel beam FBP reconstruction formula. Let us read it conceptually, not just mathematically. There are two main steps. The first step is filtering. For each projection, we apply a special filter. This filter is related to the ramp filter, whose frequency response is proportional to the absolute value of k. In spoken terms, we can say it weights the frequency component properly before reconstruction. The second step is backprojection. After filtering the projection data, we smear or backproject those filter values back along the corresponding X-ray path through the image domain. Then we repeat this for all projection angles and all the contributions to come together. By doing this, we recover the image represented by f of x and y. So parallel beam CT can be understood as a Fourier imaging method. The projection data give us Fourier domain information through the Fourier slice theorem, and filtered back projection give us a practical way to bring that information back into the image domain. That is the key idea behind the parallel beam filtered back projection method. In practice, we do not measure X-ray line integrals one by one. So that would be too slow. Instead, to make the scan more efficient, we use a point X-ray source together with an array of detector elements. In this way, we can measure a whole fan beam projection at once. With a single exposure, we can collect data along many X-ray paths simultaneously. Now, from the viewpoint of information content, fan beam geometry and parallel beam geometry are essentially equivalent. Look at the figure on the left. The thick purple line represents one particular X-ray path through the object. This same line can be measured in a parallel beam scan as one ray among a set of parallel rays, but it can also be measured in a fan beam scan as one ray coming from a point source, so the physical line integral is the same. What changes how we describe it. In parallel beam geometry, we describe a ray using two variables, the detector position r and the projection angle theta. In fan beam geometry, we describe the same ray using another pair of variables, detector position t and the source angle beta. So the same ray can be indexed in two different coordinate systems. The formulas on the right show how to convert between these two descriptions. The details may look technical, but the main idea is simple. Parallel beam data and fan beam data contain the same line integral information. They are just organized differently. This equivalence is very useful. It allows us to start from the parallel beam reconstruction formula, which we already understand, and then derive the corresponding fan beam reconstruction formula. Once we know how to convert between the parallel beam variables and the fan beam variables, we can derive the fan beam filtered back projection formula directly from the parallel beam formula. The red box shows the standard parallel beam FBP formula. The idea is simple. In the parallel beam formula, the ray is described by rand theta. In the fan beam geometry, the same ray is described by time beta, so we replace the parallel beam variables with the corresponding fan beam variables because we are changing from one pair of variables to another pair of variables. We also need a Jacobian factor. This Jacobian accounts for how the coordinate system is stretched or compressed during the transformation. After we do this change of variables, we obtain the fan beam FBP formula shown in the green box. Now, structurally, the formula is still very familiar. It is still a filtered backprojection formula. First, we filter the projection data, then we backproject the filtered data into the image domain. But compared with the parallel beam formula, the fan beam formula has some additional weighting factors. These weights are not arbitrary. They come naturally from the fan beam geometry and from the change of variables. So the main message is this: fan beam FBP is not a completely new reconstruction principle. It is same filtered backprojection idea, but modified by geometric weighting factors to account for the fan beam scanning geometry. The exact derivation of the fan beam formula can be a little tedious. So instead of going through every algebraic step, let us understand it heuristically. On this slide, we compare two formulas. The red box shows the parallel beam FBP formula. The green box shows the equispatial fan beam FBP formula. The most important difference is that the fan beam formula has several extra weighting factors. These are highlighted in green. Now, what do these terms mean? First, raise the radius of the circular source trajectory. In fan beam scanning, the X-ray source moves around the object on a circle, so this radius matters. In parallel beam scanning, there is no point source at a finite distance, so we do not need this parameter. Another important quantity is U. You can think of U as a projected source-to-point distance. It tells us how the point being reconstructed is positioned relative to the fan beam geometry. Now imagine that the scanning radius R becomes very large. In other words, X-ray source is moved very far away from the object. What happens then? The fan beam rays become almost parallel. So fan beam geometry gradually becomes parallel beam geometry. In that limiting case, the geometric weighting factors approach 1. So the fan beam formula naturally reduces to the parallel beam formula, except for one important detail, the angular range. A full fan beam scan goes from 0 to 2 pi or 360 degrees. But in parallel beam CT, pi or 180 degrees is enough because the same line integral is repeated from the opposite direction. So this gives us a very useful intuition. The parallel beam CT can be viewed as a limiting case of fan beam CT when the source is very far away. Now we can ask the reverse question. Can we start from the parallel beam formula and obtain the fan beam formula in a more intuitive way? That is what we will explore next. Okay. Before we discuss the fan beam reconstruction heuristic further, let us recall an important concept from linear system theory, the PSF. In a linear system, if we know the system responds to a point-like input, then we can predict the response to a general input. This because the general object can be decomposed into many shifted and scaled impulses. For each impulse, the system produces corresponding shifted and scaled response. Then, by the superposition principle, we add all these individual responses together to obtain the final output. This is why the response to a single point object is so important. So the point spread function tells us how a point is spread out by the system. Now, Why are we discussing linear systems here? The reason is that filtered backprojection is a linear reconstruction process. The filtering and backprojection steps are both linear operations represented mathematically by integrals. Therefore, the entire FBP reconstruction process can be interpreted as a linear system. If we understand how FBP reconstruct a single impulse or a point object, then we gain valuable insight into how it reconstructs a general image. This PSF viewpoint will help us understand the relationship between parallel beam and fan beam reconstruction more intuitively. Let us now consider a very small object in 2 dimensions. So on the slide, this is shown as the small purple point. Mathematically, we can think of this point object as an impulse or a delta function. Now suppose we project this impulse using vertical x-rays onto a detector line. In that case, the measured projection is also a point-like signal on the detector. So a point object gives a point-like shadow. Now let us change geometry. Suppose we tilt the detector line by an angle alpha. Because the detector is tilted, the same point object no longer appears in exactly the same way on the detector. Its projection is stretched along the tilted detector line. In other words, the point-like shadow is geometrically magnified. For an ordinary function, we may simply say that the coordinate is stretched. But for delta function, there is one more effect. When the coordinate is scaled, the strength of the delta function also changes. This is a basic property of delta function. The important message is this: when an impulse is projected onto a tilted detector line, its measured strength is modified by a geometric factor. This simple observation helps explain why weighting factors appear in the fan beam reconstruction formula. The geometry changes how a point-like object contributes to the projection data, and the reconstruction formula must compensate for that change. Now, let us look at the obliqueness of the detector array. First, look at the figure on the left. Suppose the red detector array is perpendicular to the purple X-ray beam. In that case, if we have a very small purple point object, its projection on the detector is also a point-like signal. Now, in fan beam geometry, the detector is not always perpendicular to every X-ray beam. Here, the green line represents the fan beam detector, and the purple X-ray beam hits this detector at an oblique angle. Because of this oblique angle, the same point object casts a stretched shadow on the detector. In other words, the projection of the point is magnified along the detector line. We call the angle between the ideal perpendicular detector and the actual detector gamma. From simple geometry, the correction depends on the cosine of gamma. On the slide, this cosine term is written as source radius divided by the square root of the source radius squared plus the detector coordinate squared. That term is exactly the weighting factor highlighted in the fan beam formula, so this factor is not mysterious. It is simply correct geometric stretching caused by the oblique detector array. Next, let us consider another effect, which is beam divergence. In fan beam geometry, the X-rays come from a point source, so the beam is not parallel. It spreads out as it travels from the source to the detector. Now imagine that we have a small purple point object near the origin. Because the beam is divergent, this small object will appear larger when it is projected onto the detector. So the delta function is magnified. This is easy to see in the figure on the left. The object is small, but its projection on the detector is scaled up. The same idea also applies when we move from a one-dimensional detector to a two-dimensional detector. So fan beam projection is different from parallel beam projection in two important ways. One is the detector obliqueness, which we just discussed. The other is beam divergence, which creates geometric magnification. Both effects must be corrected in the fan beam reconstruction formula. Now, how do we understand this divergence effect more intuitively? If the object is small, then from the X-ray source, it occupies only a small angular range. In that situation, we can use what is called a weak perspective approximation. That means we can think of the divergent projection in a simpler way. Locally, it behaves almost like a parallel beam projection, followed by a scaling operation. So instead of treating the local fan beam projection as a completely different geometry, we say first imagine a orthogonal or parallel projection of the small object. Then scale it up according to the magnification factor. This is a very useful insight. Delta fan beam projection can be understood locally using parallel beam intuition plus a scaling correction. That is why parallel beam reconstruction remains so important. It gives us the foundation, and then fan beam reconstruction add geometric correction factors. Now let us look at what happens to a very small point object when the coordinate axis is scaled. Here, the purple dot represents a tiny point object. Mathematically, we can think of it as an impulse or a delta function. Because the X-ray beam is divergent, this point is magnified when it is projected onto the detector. In the figure, the point is stretched by a scaling factor. In this example, that the scaling factor is 1/2. So the detector sees a magnified version of the point object. For an ordinary function, scaling simply stretches the shape. But for a delta function, there is an additional effect. When the coordinate is stretched, the strength of the delta function also changes. So, in simple spoken terms, if the coordinate is scaled by a factor of k, the amplitude of the delta function changes by 1/k. That is the key point. A divergent beam does not only magnify the position of a point object, it also changes the strength of the projected impulse. In fan beam geometry, this magnification is related to the ratio over u, where r is source radius and u is the projected source-to-point distance. But when we look at the fan beam reconstruction formula, this geometric factor appears as a squared term. So this one scaling effect explains only part of the formula. We still need to understand where the second factor comes from. To find the second factor, we need to look at the angular variables. In parallel beam geometry, we describe the projection direction by an angle called theta. In fan beam geometry, we describe the source position by another angle called beta. These two angles are related, but they do not change at exactly the same rate. Look at the figure on the left. Suppose we have a small point object near the origin. If the X-ray source moves by a small angle in fan beam geometry, the corresponding projection direction in the parallel beam geometry changes by a different small angle from the geometry. We can see that the small change in beta divided by the small change in theta is equal to u over r. In other words, when we convert the angular integration from the parallel beam formula to the fan beam formula, another geometric scaling factor appears. So now we have found two places where this ratio comes from. The first comes from the magnification of a point object caused by beam divergence. The second comes from the conversion between the two angular variables, theta and beta. But we still need to be careful. These two effects explain why the geometric ratio appears, but they do not yet fully explain how the factors combine in the final filtered back projection formula. So we need one more step. We need to look at what happens when the magnified projection is passed through the ramp filter. Now, why are we not done yet? On the previous slide, we found two places where the ratio U over appears. The first place is magnification of the point object caused by the divergent beam. The second place is change of angular variables from theta in the parallel beam case to beta in the fan beam case. But here is the subtle point. These two effects act in opposite directions. For the magnification effect, the divergent beam stretches the point object on the detector. To bring that magnified point back to the original scale, we need to multiply by U over R. That is the situation shown on the left side of the slide. But for the angular conversion, the situation is different. When we convert a small change in beta to a small change in theta, we divide by U over R. That is the situation shown on the right side. So one effect gives us a multiplication by U over R, and the other effect gives us a division by U over R. So as a result, these two factors cancel each other. Therefore, we are not done yet. Even though both arguments involve the same geometric ratio, they still do not explain the squared weighting factor in the fan beam reconstruction formula, so we need to look one step deeper. We should not only ask what happens to the point object before filtering, we also need to ask what happens after the projection is passed through the ramp filter. Now let us look at the correct way to understand this scaling factor. Instead of looking only at the magnified point object itself, we should look at what happens after filtering. This is important because filtered back projection does not directly back project the raw projection data. It first applies the ramp filter and then performs the back projection. So the point object and the ramp filter must be considered together. To make the idea simple, suppose the scaling factor is 1/2. In our geometry, this scaling factor corresponds to U over R. Now compare two cases. In the first case, we apply the ramp filter to the original point object. In the second case, we apply the same ramp filter to the magnified point object. Because of the scaling property of the Fourier transform, and because the ramp filter depends on frequency, these two filter results are not the same. In fact, the filter result from the magnified point object becomes 1/2 of the filter result from the original point object. This is the key observation. Once the ramp filter is included, the scaling factor appears in the denominator of the reconstruction formula. This gives us the missing factor needed to explain the squared weighting term in the fan beam formula. So the lesson is simple. We cannot analyze the projection magnification alone. We must analyze the magnification together with the ramp filtering step. Let us now look at a numerical example to make this point more concrete. Here, the red curve corresponds to the original or parallel beam-like case. The green curve corresponds to the scaled or fan beam-like case. On the left, you can see that the green gate function is wider than the red one. In other words, because of magnification, the fan beam case give us a theta function in the spatial domain. Now look at the Fourier domain on the right. So when a function becomes wider in the spatial domain, its Fourier spectrum becomes narrower. This is a basic Fourier relationship. A wider function in space corresponds to a slimmer spectrum in frequency. So the fan-beam case gives a fatter spatial function but a narrower Fourier spectrum. This is exactly what the slide title says. A fatter function gives a slimmer spectrum. This example helps us see why scaling cannot be ignored when filtering is involved. And now we apply the same ramp filter to these two cases. The important point is that the ramp filter weights the Fourier spectrum according to frequency. Since the fan-beam case has a narrower spectrum, the ramp filter result is reduced compared with the parallel beam case. In this example, the filter value for the fan beam case is half of the fan beam case. So even though the object was magnified in the projection domain, after ramp filtering, the result is scaled down. This is why the correction factor must be placed in the denominator in the fan beam FBP formula. This slide gives a visual confirmation of the analysis. The ramp filtered fan beam response is smaller, and this reduction is exactly what we need to account for in the reconstruction formula. The previous two slides showed the relationship between the two filtered results y1 and y2 at the center point where it is 0. Now this slide gives a more general analysis. Here, I use ChatGPT to check the scaling relationship symbolically. The main result is shown on the right side of the slide. The idea is this: if one function is a scaled version of another function, then after applying the ramp filter, the filtered output also follows a specific scaling rule. In this example, the scaled case gives a filtered result that is 1/2 of the original filtered result, with the coordinate scaled accordingly. So this confirms what we saw in the numerical example. Once the ramp filter is included, the ratio U over R should appear in the denominator. This is the missing piece. Now we can understand why the fan beam filter backprojection formula contains a squared geometric factor. One factor comes from converting the angular variable. The other factor comes from the scaling behavior after ramp filtering. With this insight, the fan beam formula is no longer just a complicated mathematical expression. Each weighting factor has a clear meaning, either from geometry or from signal processing. Now let us put everything together and explain the fan beam FPP formula. We have already discussed the first two weighting factors. One comes from the obliqueness of the detector array, and the other comes from beam divergence together with ramp filtering. The last weighting factor is 1/2. This one is easy to understand. In the fan beam formula, we assume a full scan over 360 degrees, but in parallel beam CT, a 180-degree scan is already enough because the same line integral is repeated from the opposite direction. So when we use a full 360-degree fan beam scan, each equivalent parallel beam line is measured twice. Therefore, we need a factor 1/2 to compensate for this double sampling. Now, if we look again at the three green shaded factors in the formula, they are no longer mysterious. Each one has a clear meaning. One correct detector obliqueness, one correct divergence and filtering effect, and one correct double coverage in the full fan beam scan. So from this viewpoint, we can understand the fan beam FBP formula heuristically from the parallel beam formula. do not have to start with a long textbook derivation. We can understand it geometrically and physically. This heuristic explanation is not only interesting, it also gives us a way to extend the fan beam formula beyond the standard circular scanning trajectory. In the textbook derivation, the fan beam formula is usually derived under the assumption that the X-ray source moves along a perfect circle. That means the radius is constant. But think about the arguments we have just used. The detector obliqueness is a local view-by-view effect. Beam divergence is also a local effect. The angular conversion is also based on the local geometry at each view. So do we really need the radius to be constant for the entire scan? From this heuristic point of view, not necessarily. Even if R changes with the fan beam angle, the same type of formula should still work reasonably well, as long as we use the correct local geometry at each view. This was the idea behind one of my early papers from my PhD research published in 1993. I called it a derivative-free, non-circular fan beam reconstruction formula. Now, I should also point out something honestly. There was a mathematical error in that paper. Because of that, the formula is not theoretically exact in the most general case, but practically it works very well. And that is why I put this little lab bug here. It is a small bug, but the idea still has a practical value. Here are some simulation results using non-circular fan beam scanning trajectories. On the top left, you can see examples of random scanning loci. Some are circle-like, and some are more triangle-like. These are not the standard circular trajectories assumed in the classical fan beam formula. The image on the top right is a true slice from the three-dimensional Logan phantom. This is the reference image we want to reconstruct. Then we apply the extended non-circular fan beam reconstruction formula. On the bottom left, we show the reconstruction using the circle-like locus. On the triangle-like locus, you can see that the reconstructed images are very close to the true slice. So even though the formula is not theoretically exact for arbitrary non-circular trajectories, it gives very good results in these numerical simulations. This tells us that the heuristic geometric interpretation is useful. It helps us design reconstruction formulas that may not be mathematically perfect, but can still work very well in practice. Here is the paper I wrote when I was about your age. As a homework, I would like you to read this paper and try to find the mathematical error. If you find it, please send me an email. I am curious to see who will be the first. This is a good exercise because reading a research paper is not just about accepting the formulas. You should always ask, what assumptions are being made? Which steps are rigorous? Which steps depend on approximation? And where could a hidden mistake appear? Even published papers can contain errors. That is a part of research. The important thing is to understand what the error affects and what part of the idea may still remain useful. So please read this paper carefully and see if you can identify the bug. In the early 1990s, I finished my PhD dissertation. My dissertation mainly addressed two reconstruction problems. The first one was the long object problem. In material science, many samples are elongated. They are not sphere-like objects that can be fully covered by cone beam projection. For X-ray microtomography, this creates a serious challenge because the cone beam projection data can be truncated along the longitudinal direction, At that time, cone beam microjection reconstruction usually required the whole sample to be completely contained inside the cone beam projection. In other words, the object had to be small enough so that there was no longitudinal truncation. But for long objects, this requirement is not realistic. To solve this problem, I derived a generalized FedCamp type algorithm for cone beam spiral CT reconstruction. The spiral trajectory allows the system to scan along the length of the object so that long samples can be reconstructed more effectively. Later, we realized that this problem was not only important for microtomography, but it also has major applications in medical imaging because the human body is a long object. It also has application in security screening, where objects such as luggage may extend along the scanning direction. So this work began as a solution to a micro CT problem, but it later became relevant to much broader imaging applications. The second problem I addressed in my dissertation was the flat object problem. In material science, many samples are not long cylinders or compact spherical objects. Many of them are flat or plate-like. For example, we may have thin material samples, fossil, semiconductor chips, electronic circuits, battery component, and other planar structures. For this kind of object, conventional cone beam CT geometry is not always ideal. If we try to scan a flat specimen in the usual way, the projection data may be incomplete or poorly conditioned for reconstruction. To solve this problem, I proposed another adapted FieldCamp pipe algorithm, this time for plate-like specimens. This approach is related to what is often called laminography. At that time, this problem came from X-ray microscopy and material science. But in recent years, it has become increasingly important. Today, flat object imaging is relevant to semiconductor inspection, fossil imaging, battery testing, and many other industrial and scientific applications. So again, we see that a reconstruction problem motivated by one field can later become important in many other areas. But now let us move from fan beam geometry to cone beam geometry. How do we reconstruct an image in the cone beam case? Again, I would like to explain this heuristically. In fan beam CT, the geometry is two-dimensional. The detector is described by one coordinate, which we can call t, but in cone beam CT, the X-ray beam diverges in 3 dimensions. The detector is no longer just a line. It is a two-dimensional plate. So now we need 2 detector coordinates. One is still t along the horizontal direction, and the other is zeta along the vertical direction. Now imagine one X-ray coming from the source. It passes through a point inside the object and then hits the detector at the purple dot. That ray is a cone beam ray. If you compare the 2 formulas on this slide, the cone beam formula in the blue box looks very similar to the fan beam formula in the green box. The main difference is in the obliqueness correction factor. In the fan beam case, this factor depends on the source radius and the horizontal detector coordinate. In the cone beam case, we also have the vertical detector coordinate, zeta. So an extra zeta squared term appears in the denominator. Now the question is, why does this extra term appear? What is the geometric meaning of this new weighting factor in the cone beam formula? That is what we will explain next. The new weighting factor in the cone beam formula is not difficult to understand. In fan beam geometry, we already had an obliqueness correction. The X-ray ray hits the detector line at an angle, and we corrected that using a cosine factor. Now, in cone beam geometry, the ray can be oblique in two directions. It can be oblique horizontally, and it can also be oblique vertically. So instead of one angular correction, we need two angular corrections. In the figure, the ray passing through the small point object makes one angle in the horizontal direction, which we can call beta. It also makes another angle in the vertical direction, which we can call alpha. The beta correction is the same kind of correction we already used in fine beam CT. But now, because the ray also tilts out of the transverse plane, we need additional correction for alpha. When we multiply these two cosine correction factors together, we obtain the cone beam obliqueness factor shown in blue. This is why the cone beam formula contains the additional zeta squared term. So the new weighting factor is not mysterious. It simply comes from the fact that a cone beam ray is oblique in three-dimensional space, not just in a two-dimensional fine beam plane. There is another way to understand the similarity between the fine beam and the cone beam formulas. Suppose we want to reconstruct transverse slice. If we had perfect fine beam data exactly within that slice, then we could simply use fine beam FAP formula slice by slice. But in cone beam CT, for a given point in the object, the actual measured ray may not lie exactly in the transverse slice. Instead, the ray belongs to a tilted fan. It passes through the point, but it is tilted relative to the desired slice plane. Now, if we look at this tilted fan from the top, its projection overlaps with the fan beam we would like to have in the transverse plane. So we can use the real cone beam ray to approximate the imaginary fan beam ray in the slice. The price we pay is that the ray is tilted. Therefore, we need a cosine correction to compensate for this tilting effect. This is the correction associated with the vertical angle alpha. The horizontal correction associated with beta is already included in the fan beam formula. Cone beam data mainly requires one additional obliqueness correction for the out-of-plane tilt. This gives us a very intuitive explanation of how cone beam data can be converted approximately into fan beam-like data for slice reconstruction. So although this cosine correction or obliqueness correction is approximate, it often works very well in practice. The idea is that each cone beam ray is corrected according to its own local geometry. For a particular point in the object, we look at how the ray is tilted relative to the desired transverse slice, and then we apply the corresponding correction factor. This makes the correction point specific and adaptive. It is not just one global correction applied everywhere. It changes depending on the ray direction and the point being reconstructed. That is one reason why the cone beam approximation can produce excellent reconstruction results, even though it is not theoretically exact in the most general case. So again, the heuristic picture is very useful. We start from the fan beam formula, then add the extra correction needed for the three-dimensional cone beam geometry. This helps us understand why the cone beam reconstruction formula has the form shown here. So although this cosine correction or obliqueness correction is approximate, it often works very well in practice. The idea is that each cone beam ray is corrected according to its own local geometry. For a particular point in the object, we look at how the ray is tilted relative to the desired transverse slice, and then we apply the corresponding correction factor. This makes the correction point specific and adaptive. It is not just one global correction applied everywhere. It changes depending on the ray direction and the point being reconstructed. That is one reason why the cone beam approximation can produce excellent reconstruction results, even though it is not theoretically exact in the most general case. So again, the heuristic picture is very useful. We start from the Fan-Beam formula, then add the extra correction needed for the three-dimensional cone beam geometry. This helps us understand why the cone beam reconstruction formula has the form shown here. So far, I have explained the key ideas behind approximate fan beam and cone beam CT reconstruction. Naturally, the next question is, can we do exact cone beam reconstruction of a three-dimensional object? To approach this question, let us first go back to a simpler case. Since approximate cone beam reconstruction was developed from parallel beam and fan beam formulas, we begin by thinking about two-dimensional parallel beam projections recorded on a detector plane. This can be viewed as a limiting case of cone beam geometry, where the cone angle becomes very small. The simplest scanning strategy is to rotate the two-dimensional parallel X-ray beam around a fixed axis over 180 degrees. In that case, this three-dimensional problem can be decomposed into many two-dimensional reconstruction problems. Each transverse slice, such as the green rings shown on the left, can be reconstructed using the two-dimensional parallel beam or fan beam method we already know. But in three-dimensional space, we are not limited to rotating around only one fixed axis. We can illuminate the object from many different orientations. In principle, the projection direction can follow a much more general trajectory. The Mobius strip shown here is a way to suggest that the possible orientations of projection planes in three dimensions are richer than in the simple two-dimensional case. Now, do we have a Fourier slice theorem in three dimensions? Yes, we do. Based on the same heuristic reasoning we use for the two-dimensional Fourier slice theorem, we can immediately understand the three-dimensional version. Consider a three-dimensional object shown here in red. Suppose we take a two-dimensional parallel beam projection of this object along the thick orange direction. This projection is a two-dimensional image on a detector plane. Now, if we take the two-dimensional Fourier transform of that projection, we obtain a two-dimensional slice in the three-dimensional Fourier domain of the object. This Fourier slice is orthogonal to the projection direction. So the idea is very similar to the two-dimensional case. In 2D CT, a one-dimensional projection gives us a line in the two-dimensional Fourier space. In 3D CT, a two-dimensional projection gives us a plane in the three-dimensional Fourier space. This Fourier plane contains the wave components of the original three-dimensional object that are perpendicular to the projection direction. Therefore, if we collect many two-dimensional parallel beam projections from many different directions, we collect many planes in the three-dimensional Fourier space. If these planes cover the whole Fourier domain, then we can reconstruct the object by inverse Fourier transform. This gives us the wave-based view of exact three-dimensional reconstruction. Now let us ask a more interesting question. What happens if the projection direction does not simply rotate around one fixed axis? What if it follows an arbitrary three-dimensional trajectory? The key observation is this: as long as the normal vector of the projection plane starts in one direction and ends in the opposite direction, the collection of Fourier planes can still cover the entire three-dimensional Fourier space. In other words, the projection plane may rotate, tilt, or wobble in a complicated way. But if its normal direction is continuously inverted, then every point in Fourier space will be crossed by at least one of these planes. This is the scan insight behind the Orlov theorem. So the exact shape of the trajectory is not the only important thing. What matters is whether the family of projection planes sweeps through the Fourier space completely. If the normal vector goes from one direction to the opposite direction continuously, then the scan can provide sufficient Fourier information for exact reconstruction. Let me try to convince you of this idea geometrically. Look at the left side of the slide. Imagine a plane in Fourier space. We color the top side of this plane red and the bottom side blue. Now suppose the normal vector of this plane starts along the positive k3 direction. Then we continuously rotate the plane until the normal vector points in the opposite direction. When this happens, the side of the plane that you see from above changes. Initially, you see the red side. After the normal vector is turned upside down, you see the blue side. Now think about any point in Fourier space. If a red point initially lies on one side of the plane and later ends up on the other side relative to the moving plane, then the moving plane must have passed through that point at some moment. That means the Fourier value at that point has been measured by one of the projection planes. The same reasoning applies to the blue points on the other side. For the orientation to be completely inverted, the moving projection plane must sweep across the Fourier space. This is the essence of the Orlov theorem. If the normal vector of the projection plane is inverted continuously, then the collected projection data are sufficient, at least in the parallel beam setting, for exact reconstruction by inverse Fourier transform. So the Orlov theorem gives us a powerful scan condition. It tells us when a three-dimensional parallel beam scan contains enough information for exact reconstruction. Next, let us see how the Orlov theorem helps us understand exact spiral cone beam CT reconstruction. First, we need to introduce a few elegant and very important concepts. The first one is a PI segment. A PI segment is a line segment whose two endpoints lie on one turn of the helical source trajectory. A beautiful property is that every point inside a long object covered by the helical scan lies on one and only one PI line. The portion of the helix between the two endpoints of the PI segment is called the PI arc. Then we have a time window, also called the Thom-Danielson window. This is the detected area on a cylindrical surface bounded by two neighboring turns of the helix. This window tells us which part of the cone beam detected data is needed for exact reconstruction. Now, let us think about the small blue ball shown here. We can view the PI segment as something like a diameter passing through a small local region. The blue ball is illuminated by X-rays from the source positions along the PI arc, and the corresponding data are recorded in the time window. If these were ideal two-dimensional parallel beam projections, then by the Orlov theorem, the small blue ball could be exactly reconstructed. But in real spiral cone beam CT, we do not have parallel beam projections. We have cone beam projections. So the question is, can we still get exact reconstruction? Here is the key heuristic argument. If the parabol is very small, then locally the cone angle is also very small. In that locally beam projection can be approximated by a parallel beam projection after applying the proper scaling and weighting corrections. This is the same weak perspective idea we discussed earlier. So for a very small point-like object, we can convert the local cone beam data into the corresponding parallel beam data as accurately as needed. That means exact spiral cone beam reconstruction of a small local object is feasible, at least from this weak perspective point of view. Based on this idea, we can heuristically understand and even rederive the Catswich exact cone beam spiral reconstruction formula. Let me elaborate on that point. The small blue ball I mentioned on the previous slide can be located anywhere inside the volume of interest. It is not restricted to one special location. So, in principle, any small local target inside the object can be reconstructed exactly from the cone beam spiral data, provided the required PI line and time window data are available. Now remember the Fourier slice theorem. The reconstruction by inverse Fourier transform is a linear operation. If we can reconstruct one small ball exactly, then we can reconstruct many small balls exactly, and by superposition, we can reconstruct the entire object. So the whole object can be thought of as a collection of many small local targets. If each of these local targets is properly concatenated by the cone beam data on the time window, then the complete volume can be exactly reconstructed according to this Orlov type reasoning. Now compare this with approximate cone beam reconstruction, such as a generalized field cam algorithm. An approximate algorithm cannot reconstruct each small ball perfectly because it uses approximate obliqueness correction and approximate geometric compensation. So for example, instead of reconstructing a point-like ball as a clean point, it may reconstruct it as a small star-like pattern. Then, if the object contains many small balls, the approximate algorithm reconstructs many small stars. When these errors are added together, they generally do not cancel perfectly. As a result, we obtain an approximate reconstruction rather than an exact one. There are special cases where error cancellation can happen. For example, a longitudinally homogeneous long object may be reconstructed very well by a generalized Feldkamp type method. But in the general case, approximate corrections lead to approximate reconstruction. This comparison helps us understand the difference between approximate and exact cone beam CT algorithms. The original papers on exact spiral cone beam CT reconstruction are filled with complicated formulas and many derivation steps. Mathematically, one can follow those derivations line by line. But for imaging engineers and students, the motivation behind those formulas is not always obvious. It can be difficult to see why the formula should have that structure, or why certain geometric objects such as pylines, PI arc, and the time window appear naturally. What I have tried to do here is to reveal the intuition behind the mathematics. We started from parallel beam CT, then moved to fan beam CT, then cone beam CT, and finally spiral cone beam CT. Along the way, we used several viewpoints: impulse functions, Fourier analysis, weak perspective, obliqueness correction, the Fourier slice theorem, and the Orlov theorem. With these ideas, the exact cone beam formula becomes less mysterious. We can appreciate the essential reason why exact reconstruction is possible, even though the final mathematical expression may still look quite complicated. So the goal here is not to replace rigorous mathematics. Rather, the goal is to make the mathematics understandable and meaningful. Finally, let me mention that cone beam CT remains a very unique and important area. It is unique because it combines several difficult issues at the same time: beam divergence, three-dimensional geometry, helical scanning, and data truncation. These issues make the reconstruction problem mathematically challenging. At the same time, it is very important because cone beam spiral CT has many practical applications. It is central to modern medical CT, and it also appears in industrial imaging. security screening, micro-CT, and other areas. Here I show some of our work on triple source spiral cone beam CT in collaboration with Professor Kasevich and other colleagues. The idea is to use multiple X-ray sources to improve data acquisition and reconstruction performance. These examples show that the field is still active and full of interesting problems. Even though much progress has been made, there are still many opportunities to develop new reconstruction methods, new scanning geometries, and new theoretical insights. So cone beam CT is not only a classical topic, it is still a rich area for future research.